3D modeling and printing are taking the do-it-yourself world by storm as makerspaces spring up in many schools. Considered to be an innovative way of learning next-generation skills, 3D modeling and printing are fun hobbies, but are they effective educational tools? Is 3D technology worth the cost and the time it takes to learn? Is 3D printing just another new toy, or is it a pedagogically sound method for deep learning? My name is David Black, and I've taught media design classes for 30 years at the secondary level. I have developed multidisciplinary projects that combine 3D modeling with science, but what I've lacked is a theoretical framework. This video explores the history and innovation of 3D modeling and printing from a constructivist framework within a project-based learning pedagogy to teach science concepts. We will look at the diffusion of this new technology, how it works as a medium to convey learning, the basic steps and history of producing 3D models and prints, and provide examples of 3D technology use in science classrooms. When students create their own science educational content or learner-generated digital media, they achieve a deeper understanding of science. Researchers have found that students not only learn science content well through media creation, they also develop marketable media design and 21st century skills of collaboration, communication, critical thinking, and creativity. Reina and Meyer in 2018 conducted a literature review of studies that used learner-generated digital media to teach science concepts. They concluded that previous studies were limited because they lacked theoretical frameworks or sound pedagogy. These studies assumed that the students already knew how to use media design technology tools, since they were so-called digital natives. According to Reina and Meyer, just because students grow up using computers and digital devices doesn't mean that they have ever developed media creation skills, such as video editing or 3D modeling. In a follow-up study, Reina scaffolded media design creation skills through smaller partial projects. These projects were embedded in a theoretical framework of constructivism and a project-based learning pedagogy. Once the small-scale project is completed, the students will be ready to tackle the large-scale project. Constructivist theory proposes that learning is a socially mediated cognitive process whereby learners experience a subject and construct their own meanings for it. They create mind maps or schema that tie previous learning, emotions, and social reinforcement together with their new knowledge. Constructivism demands that the learner is at the center of the process. 3D modeling is inherently a constructivist activity, as creating the models literally requires constructing one polygon or primitive at a time. That the model exists only in virtual space does not mean it is any less a constructed medium. If properly planned and conceived, students can also construct science knowledge through 3D modeling and animation. Instead of consuming scientific content, students become producers of content. They become the experts and the teachers, and learning occurs as a natural byproduct of the process. Constructivist theory can be traced all the way back to Socrates, who said, "Education is the kindling of a flame, not the filling of a vessel." John Dewey proposed that students learn by doing, that is, in an active, creative process where they construct their own meanings through discovery, with the teacher as a guide on the side, not a sage on the stage. It is the opposite of objectivism, where teachers are the center of the process and must somehow pour their knowledge into their students' brains. Lev Vygotsky added that learning is socially mediated through interpersonal interactions, language, and culture, and that students learn within their zone of proximal development. As students learn more, then their zone of proximal development expands. Jean Piaget developed cognitive constructivism, where children develop naturally through various stages from concrete to abstract, with each stage of cognitive growth affecting the construction of learning. Seymour Papert developed his constructionist theory, where students construct learning through making. He saw computers as a tool for learning and invention, where students learn through doing and experimentation, including the use of computer programming and media design. Today's makerspaces are based on his theories. Project-based learning is a natural fit as a pedagogy for media design creation. It usually occurs in teams, and the conclusion is a public product. According to PBL Works, formerly the Buck Institute for Education, gold standard PBL includes 7 characteristics. 1. A challenging, meaningful question or problem to address. 2. Student inquiry using authentic data or sources where they discover the learning for themselves as a natural outgrowth of the initial question. 3. Student voice and choice in the type of project chosen and how it will be accomplished. 4. Collaboration and communication as students actively participate and work through issues creatively. 5. Frequent opportunities for critique and formative feedback with revision. 6. A public presentation of the final product. And 7. Student reflection on what they have accomplished and learned. Knowing that their work will have a public audience motivates students to deliver a high-quality product and helps to actively engage them in the process of learning. As John Spencer, a well-known PBL guru, explains, students who engage in authentic project-based learning have increased agency and ownership. They're often more excited and engaged in their learning. When this happens, they retain the information for a longer amount of time, while also learning vital technology skills like digital citizenship and media literacy. However, they also learn vital soft skills such as collaboration, communication, curation, and problem solving. As they work through iterations and revise their work, they develop a growth mindset. Often, they learn how to seek out constructive feedback. This connection to the community can help them develop empathy. There's been a long-standing debate about which is more important, the medium or the message. In the early 1960s, Marshall McLuhan created the concept of the global village, which predicted the interconnectivity of the World Wide Web. He famously stated that the medium is the message. Such technologies as print and movable type have a profound effect on the human psyche and cultural understandings. Humans reinvent themselves and how they communicate with the development of each new medium. Richard Clark argued conversely in the 1990s that the medium of a message was unimportant to the learning process, and that cost-effectiveness was the only consideration in choosing one medium over another in instructional design. If more than one form of media can be used for a particular learning task, then they are replaceable with each other, and the medium does not influence the message. Kozma in 1994 took a middle ground where the medium conveys or mediates the message, influencing the message because of the medium's unique affordances, advantages, disadvantages, limitations, and conventions. Learning from a video with its linear format is qualitatively different than learning from interactive media, such as a website or a CD-ROM-based multimedia title. 3D modeling and animation has its own affordances that allow it to present a unique learning experience, unlike other media. It can visualize large datasets, allowing patterns and interrelationships between data to be understood in a way that purely numeric data tables cannot. The medium chosen to convey learning is therefore an essential part of the learning experience. This agrees most closely with Kozma's middle ground on the Clark-McLuhan continuum. With all of this in mind, let's now turn to an examination of the history of 3D modeling and printing as an innovative technology and how it can be used in a science classroom. Computer graphics began in the 1960s with a doctoral thesis by Ivan Sutherland, where he demonstrated Sketchpad, a program that used a light pen to draw directly on a computer monitor. His friend Dave Evans convinced Sutherland to join him in starting a computer science program at the University of Utah. Flush with money from the DARPANET project, Evans and Sutherland recruited some of the most promising computer science graduate students in the country, including Ed Catmull. Their team developed a method called ray tracing to render realistic, smooth, polygonal surfaces, such as the famous Utah teapot. As microprocessors improved and computer speeds and power increased, the first entertainment applications appeared. Disney Studios created 3D graphics sequences for Tron, the first movie with extensive CGI. The Last Starfighter brought even more photorealistic effects, with complete armadas of spaceships, planets, and asteroids. Meanwhile, some of the artists that started with Tron founded their own studios, including Robert Abel and Associates, who created a number of iconic and Clio Award-winning TV commercials. This included the famous 1984 Super Bowl Sexy Robot commercial that introduced innovative motion capture technology. Lucasfilms and Industrial Light and Magic experimented with completely 3D animated short movies. When Steve Jobs left Apple Computers and invested in the studio, they became Pixar Animation Studios and created the groundbreaking Luxo Junior Animation. Jobs encouraged John Lasseter to create a full-length 3D movie. The result was Toy Story in 1995, and the rest is history. In 1981, Hideo Kodama of Nagoya Municipal Industrial Research Institute published a description of a liquid resin-based photopolymer. This polymer becomes solid when it is exposed to ultraviolet light, but he did not file a patent. In 1984, Charles Hull invented a similar system called a stereolithography apparatus, or SLA. Refinements continued, including building up layers by sending UV light in cross-sections. The type of 3D printing most familiar in schools is the fused deposition modeling technique, where a plastic filament on a spool is fed into the printer by a motor, melted by a heated nozzle, and deposited in layers continuously to make cross-sections. This type of printing was first developed in the late 1980s by F. Scott Crumb, who went on to found Stratasys in 1990 as the first company to build FDM printers and plastic filament. Altogether, these technologies are referred to as additive manufacturing because the models are built up or added layer by layer. By comparison, a 3D milling machine or CNC router uses subtractive manufacturing because it starts with a larger blank and carves away parts. By 2009, new companies entered the market with lower cost 3D printing machines such as MakerBot, SourceForge, Prusa, and Ultimaker. Various types of plastic filament became available, including polylactic acid, acrylonitrile butadiene styrene, and even flexible nylon filaments, fused metallic filaments, and water-dissolvable filaments for printing supports. Filaments come in many colors and finishes, including filaments that change color as they spool into the printer. A new development is 3D printing in full color. However, these printers cost about $3,500 or more. To print in color, 4 processed color dyes are added to a base white filament as it extrudes. Many 3D models are available for free online, but ultimately the fun of 3D modeling is to do it yourself. Complicated by working in 3-dimensional space on a 2-dimensional computer screen, 3D modeling starts with primitive objects such as spheres, cubes, and cylinders that are given textures and composed into scenes. They can be combined to add, cut, or intersect each other using Boolean commands. Other objects are created using a polygonal mesh like chicken wire. Meshes act as 3-dimensional vectors that can be subdivided. Grayscale images can be converted into terrain objects with light areas as mountains and dark areas as valleys. To create complete scenes, the objects are aligned and composed, the camera positioned, lighting and atmospherics provided, then the scene rendered out through ray tracing, as if the scene were being photographed by bouncing a beam of light out from the camera. To animate objects, a timeline is added, and the objects are given hierarchical links from parent to child. The pieces can be moved, rotated, and otherwise changed over time by adding keyframes on the timeline. The computer then renders out an animation frame by frame, creating all of the in-between frames itself. Complex characters can be rigged with bones and joints or morph targets to deform the polygonal structure over time. Learning 3D animation is traditionally a difficult and time-consuming process. Teaching students how to do all of these steps competently can take several weeks of class time, which few teachers can afford to do. However, new tools are simplifying the process. Tinkercad is a browser-based modeling tool that has a range of primitive objects and simple textures that can be combined into more complex models, which can then be exported and printed with a 3D printer. SculptGL is another browser-based modeling tool. It does create complex meshes, but instead of subdividing polygons one at a time, the tool works as a ball of virtual clay that can be pushed and pulled. Reina's 2018 literature review concluded that most previous studies lack a good theoretical framework or solid pedagogy. This agrees with the TPAC model of technology integration. There are three things that need to be considered: the affordances and workflow of the technology, the appropriate pedagogy for teaching it, and how students learn content knowledge through the technology. By using a constructivist, constructionist framework, a project-based learning pedagogy, and by teaching students how to create media as they learn science content, we are following the TPAC model. For 3D modeling, we cannot assume that even digital natives know how to use the conventions of modeling in three-dimensional space. This is highly technical work and requires practice and scaffolding by using simpler projects before large-scale media projects can be undertaken. We have to remember that the purpose of using 3D modeling to teach science concepts must be worth the time and the effort and cannot be taught adequately in any other way. Because of these challenges, 3D modeling and printing have been slow technologies to truly take hold in schools. Although 3D printers are popular now, most schools and teachers have little idea how to use them effectively. If we use Everett Rogers' model of technology adoption, schools are usually in the late or laggard phase for adopting 3D technologies. One of the most important reasons for using 3D modeling in a science classroom is to visualize scientific data. To demonstrate how to do this, my chemistry students this week studied electrochemistry by comparing the voltages of different combinations of metal electrodes. They recorded the data in a two-dimensional grid separated by commas. We used a free program from the National Institutes of Health called ImageJ to convert the raw numbers into a grayscale image, with higher values represented as lighter shades of gray and lower numbers as darker shades. The grayscale height map is added as a terrain object in 3D software. As an example of building models to illustrate concepts, in 2004 my media design students began work on a video documentary for KUED, Salt Lake City's PBS station, on the history of AM radio in Utah. They created animations of transistor radios as part of the title sequences for each video segment. Other examples include modeling the SOFIA aircraft, or Stratospheric Observatory for Infrared Astronomy, creating models and animations of Mars space probes, accessing 3D altitude data of Mars from the MOLA instrument to create models of possible human landing sites, and collaborating with the NASA Lunar Science Institute to create animations of features and the formation of the moon. For a unit on the history of chemistry, my students modeled Greek philosophers and their theories about matter. Using data about the periodic properties of the elements, my chemistry students used ImageJ to create 3D models so that they could visualize the periodic trends. My biology students used Tinkercad and SculptGL to create viruses for a unit on microbiology. To represent landforms on Earth, my students accessed Earth Explorer by the United States Geological Survey. They downloaded shuttle radar topography mission data and then converted it into highly accurate 3D models. All of these examples took time to learn and execute, so we needed to have compelling reasons for using 3D modeling that were worth the opportunity cost of time and the steep learning curve. In each case, using 3D enabled us to present authentic data more completely and helped us visualize important scientific concepts more effectively than other types of media. Using 3D modeling has benefits for students. Visualization of big data sets has become a growth career, as has 3D printing of everything from prosthetic limbs to cars to rocket parts. It allows for rapid prototyping and has become a necessary tool set for engineers. My students have used these techniques to create visuals for winning science fair projects. As part of the Mars Exploration Student Data Team program, my students downloaded Mars dust opacity data and converted it into animations showing how a dust storm rose up over the Tharsis Plateau, blew across the equator, and spread globally just as the Mars exploration rovers were approaching. They got to present their animation at a symposium for students at Arizona State University. My current physics students are using altitude data from the Lunar Reconnaissance Orbiter's LOLA instrument. They are turning grayscale height maps of the moon into 3D models and then overlaying spectroscopic data so that they can find out where different commercially viable minerals might be located. They are creating a poster of their results for the ExMASS program to compete with students from 9 other schools across the country. In this video, I've described a lot of examples of excellent projects that my science students have created using 3D modeling. Not only have they learned a lot about science, they've also learned a lot about collaboration, creativity, cooperation, and communication. They've learned about STEAM careers and how to use these marketable skills. Given our limited time as teachers and the high opportunity cost, we have to be very sure that 3D modeling enhances science learning in ways that other technologies cannot. In my own experience, the projects have been well worth the time and effort. Other teachers will have to look at their own situations and decide if it is worth investing the time and the effort to use 3D technology in their own science classrooms. Thank you for watching.